So problem number 1 says I have a 7.83 gram sample of HCN, which has 0.290 grams of hydrogen and 4.06 grams of nitrogen. Find the mass of carbon in a different sample of HCN. So this question is based on the law of conservation of mass. And it's giving you information on one sample of HCN, but asking you about a second sample. So based on the law of conservation of mass and what you know about compounds, if I have a sample of a compound and I have a different sample, they're both the same material. So whatever I do with one, I can do with the other. So, and because of the law of conservation of mass, the mass that I have had to be accounted. So if I know the mass of hydrogen and the mass of nitrogen, I also know the mass of carbon in that sample because it's the difference from the total mass. From that, let's do that first part just. So in sample number 1, grams of carbon is going to be that 7.83 minus 0 minus 4.06, which is 3.48. So I had 3.48 grams of carbon in a sample of 7.83 total. How can I use that to determine how much carbon there is in 3.37 grams in a different sample? Any ideas on how can I do that? Yes?
Take that percentage out of the second sample of these.
That's exactly what you need to do. Very good. So the percent of carbon is at 3.48 divided by 7.83. So it's around 0.444% carbon. So now, knowing the law of conservation of mass and knowing that Dalton said that if I have one compound, you have two different samples of the same compound, they're the same compound because they're made of the same thing. So if the percent of carbon in sample number 1 is 0.444%, the percent of carbon in the second sample should be the same. So if I take 0.444 times 3.37, I can calculate that I have 1.50 grams of carbon in sample number 2. That 1.50 is going to give me the same percent by mass that I had in the first sample. So I can compare both that way. So I like this problem because it incorporates two different things, percent by mass, which is a simple mass calculation. It's a simple percent calculation. And it uses the theories from the scientists and put them into practice. So don't forget the conservation of mass. And then if a sample is made of the same type of elements, I can have two different samples as long as they have the same ratio, the same percentages, they're the same type, the same compound or the same sample. So don't forget how to do that one. Now, this one, sample problem number 2, says write the isotopic symbols for each isotope using both representations. For a nickel isotope of, okay, this one, we haven't talked about isotopes yet, so this one is out of place, so we'll come back to this one. Let's work on the table together. And this is a good segue point to what we have to do next. So the first column is just Z, which is the atomic number. A is the mass number, and then you have number of protons, electrons, and neutrons. The charge and the symbol, that one, we haven't done charges either, but we can do the other columns together. Okay, so I only have 34 neutrons, and I have copper, because I have copper. And where did I put my periodic table, which I didn't bring with me? I always forget something. Oh, thank you. Copper is 64. Actually, you know what? This table has isotopes in it, so we cannot do it quite yet. So we'll come back to it. Okay, so now we can go back to that problem number 2. It says write the isotopic symbol for each isotope using the representations. So I have a nickel isotope with 30 neutrons. So nickel is Ni. I'm going to write it in 2 different ways. The first one is the symbol, where I put the mass number and the atomic number in it. To be able to do that, I need to know what the atomic number of nickel is, which is 28. And because I have 30 neutrons, the mass number is going to be 30 plus 28, which is 58. That's the first way I can represent that isotope of nickel. The second way is just a symbol with a dash and the mass number. Or I can also say nickel 58. If I give you the isotopic symbol, or I give you the name with a dash and the mass number, you have to use that information to calculate neutrons. You cannot use the periodic table, because then the particles are going to be calculated incorrectly. So you have to use the information given first to calculate particles before you can use the periodic table. The only thing that you can use the periodic table is calculating the number of protons. That is not going to change ever. Okay, so now if we have argon is element number 18. So 18 plus 21 is 39. So argon 39, 18, that's my isotopic symbol, or AR 39, or argon 39. I wanted to have this problem in here because we have to get good at reading this. So number of neutrons is top minus bottom. 39 minus 18 is 21 neutrons. And because I am specifying that mass number, I have to use that to determine neutrons. Protons is always going to be 18. So I can, in all theory, I can write that as argon 39, and that 18 is implied by having the symbol there. If you notice, these atoms that I just did, these two, the nickel and the argon, are neutral because you don't see any charge in it. So that means the number of protons and electrons in these 2 cases are going to be the same, because protons equals electrons. Alrighty. So now we are ready for the table. We have Z, which is the atomic number. We have A, which is that mass number, protons, electrons, neutrons. So I have 34 neutrons, and the symbol is copper plus 2. So copper is element number 29. So the number of protons is 29. Z is also going to be 29. And because the number of neutrons is 34, 34 plus 29 is 63. Number of electrons, well, I have a +2 charge. So if I have 29 protons, the number of electrons is going to be 27. 2 less. When it's positive, you have less electrons. How many? Whichever the charge is. So it's a +2, so I have 2 less electrons. So the charge is +2. Okay. My second one, Z is 16. What element is, yes?
Sorry, so what does the A stand for on the table?
A is a mass number. So what element is 16? Sulfur. So I know it's going to be an S. So the number of protons is also 16. And because I have 18 electrons, I have more electrons, so the charge is going to be -2. Because I have 2 more. And the number of neutrons is 32 minus 16, which is also 16. Okay, let's do one more just so we know how to complete the table. I'm not going to do the whole table. Let's do the fourth one, the one with a -1. So I know it has a -1. The number of electrons is 36, so the atomic number should be, if the charge is -1, the atomic number should be it has 1 more electron that it should. So if the number of electrons is 36, the number of protons is 35. It has 1 less. So atomic number 35 is bromine, so that's Br. So now we only have the mass number. Okay, that Z is also going to be 35. The number of neutrons is 81 minus 35, which is 46. Again, use the information that is given to you to fill out the table. And then if you don't have any other way to calculate the rest of the particles, then use the periodic table. I will use the periodic table last. So let's make sure of that. Okay, so let's move on because we want to make sure we cover all the type of problems you can have. The rest of the table, I believe you can do by yourself. So I told you that I can use an instrument in lab to determine atomic mass of the element. So what you do is you take a sample, you put it, I think depends on the sample, you have to prepare it in a certain way. So when you put it in the instrument, it's going to bombard it with some rays, and it's going to create a spectrum. That spectrum is going to give you the percent abundance of all the isotopes for that element. And also it's going to give you what the atomic mass of that isotope is going to be. So for isotope number 1, I have a reading that says 60.9. 60.9. 68.9, because it says the intensity of 100. It's giving you the twin sensitivity. Okay, let me slow down. The following mass spectrum was plotted. Gallium-69 peak has an intensity of 100, and gallium-71 has an intensity of 66.4. Knowing the atomic masses of each one of the isotopes determine what the average atomic mass of the atom will be. So I told you that the weighted average mass atomic mass of that element is a percent abundance times the atomic mass. I'm gonna do a summation in here because it's for every single one of the isotopes. So you have to do that. Percent abundance of isotope number 1 times atomic mass of isotope number 1. Do the same for number 2 and so on. So the only thing that we don't have in here is a percent abundance for each of the isotopes. But I can determine that by looking at the intensities. If you add all the intensities together, I get a total intensity for the atom. So I can calculate the percent as the intensity for any particular isotope divided by the total intensity. That's going to give me, if I multiply by 100, that gives me a percent, or I can leave it without multiplying by 100. It gives me a decimal, which is what I need. So the weighted average mass is going to be 68.9255H, which is isotope number 1, times the percent abundance of number 1. The percent abundance of number 1 is going to be 100 divided by 166.4. And all I did was add the two intensities together to get the total intensity, plus the mass of the second one times the intensity of the second one, which is 66.4 divided by 166.4. And when I do the math, I get 69.71 AMUs, because I told you any measurement needs units for now. We are going to say that the units of the atomic mass are going to be atomic mass units. That's going to change next week when we get to the next chapter. But for now, because we need units, we are going to call them atomic mass units. Sometimes I use the symbol U for AMUs. So depending on which book you read, you might see it both ways. Again, because we're calculating the weighted atomic mass of this element, and normally what you get are graphs like this that show the intensity. The percent abundance comes from the intensity of that particular isotope divided by the total intensity of all the isotopes. And once you get those percentages, you can use the masses, because the diagram gives you those masses, and determine the average mass that way. That's how it's done in a lab. Now, we can also look at it like this. You have silver, which has 46 known isotopes, but only 2 happen naturally. Silver 107 and silver 109. Given the following mass spectrometric data, calculate the atomic mass of silver. So now I have a table that has the mass of each isotope with the percent abundance of each isotope. So this is a more straightforward, a more typical way of you seeing the data provided. So you need percent abundance, you need the atomic mass of each isotope to solve for weighted atomic mass. So weighted atomic mass is 106.90509 times the percent abundance in decimal form. To get it in decimal form, you have to divide by 100. Don't forget that. Plus 108.90476 times 0.4816. you end up with a mass of 107.87 for silver. When you look at the atomic mass that you calculate and compare it to what's in the periodic table, that answer should be the same value. Now, depending on how many decimal places you use and which periodic table you use, that number could vary a tiny bit, but that's okay. That's just more of a precision thing than an accuracy thing. But for the most part, that value should be close in there. And because the percent abundance of the first isotope is closer to the atomic mass in the periodic table, you know that that one contributes the most to the total mass, because I have 106.9 and the mass is 107. That's pretty close. So I know that silver 107 contributes the most to the overall mass of the atom. Now, I have two more problems that I'm going to set up. I am not going to solve them because I want you to see how they are solved. Okay, copper has two isotopes, copper 63, copper 65. If the mass of copper 63 is 63.546, actually no. If the mass of copper is 63.546, what is the percent abundance of each isotope? So in here, I'm giving you the masses of the isotopes, but I am not giving you the percent abundance. But I am giving you a piece of information that's as valuable as well. It's telling you the atomic mass is 63.456. Can I use that to determine the percent abundance of each isotope? How? Don't say yes or no, just, I'm going to follow up with a how. And that's what I want to show you. The weighted average mass, which is the atomic mass, is a percent abundance times the isotope mass. That's the equation. I'm looking for a percent abundance. When you're in math class and you're looking for an unknown, what can you replace the unknown with? X. That's what we're going to do here. Do I know the weighted average mass? Yes, because that's given as 63.546. So isotope number 1 is X times the mass plus the mass of the second one Can I put X in there? X is the percent of the first isotope. Can the second isotope have the same variable? No. There's one more piece of information you know. When we're dealing with percentages, the percent has to add to what? A percent always add to what number? 100. So if I'm using a decimal X for the percent abundance, the other one has to be 100 minus X. If I use the percent value. If I use the decimal form, I can use S and 1 minus X. And now it's just an algebra problem. Has nothing to do with chemistry. All I had to do is propagate those values, multiply combined terms, leave the X alone, and solve for X. And when you do that, X is going to be 0.695, which is 69.5% abundance. Copper 63. So 1 minus 0.695 equals 0.305 or 30.5% for copper 65. So make sure that you know how to go from the setup to the answer. So go through the math. In case I give you a problem like this in the test, you know how to solve it so you don't get stuck through the math. Okay. Any questions on this one? Do you see what I did? Does it make sense? That's the biggest question. As long as it makes sense, I'll move on. Okay, so now look at this one before I tell you how it's done. See if you can figure it out. I have an element with 3 natural occurring isotopes. Calculate the atomic mass of isotope number 3 based on the information provided. So I have a small table with the mass and the percent abundance for isotope 1 and 2. For isotope number 3, I don't give you anything. I have to come up with the mass. I have to come up with a percent abundance for isotope number 3. Which one of those two things is the easiest one to calculate? The percent abundance of isotope 3, because percent abundance is going to be 100 minus 92.2 minus 4.67. What's that? 3.13. Okay. So now that you have the percent abundance of isotope number 3, the problem is pretty much set up for you because you have everything but the mass of isotope 3. So what can I do again? Call it X. So when you set up is, now there's one more piece of information that I don't have, is the weighted atomic mass of copper. But I can look where to get that information. The periodic table. So what is the mass of copper? It should be 28.085, I think. No. 63.54. Am I looking at the same problem? So it's not 28, should be 60. So the atomic mass comes from the periodic table. The first isotope, you have everything you need. The second isotope, you have everything you need. The third isotope, the only thing that you're missing is the mass of the isotopes, which I'm calling X. You have a more straightforward equation where you're solving for X. Should be around 30.2 AMUs, if I did my math correctly. Again, I am going to let you go through that yourself so you know how to solve it yourself. So give it a try. Okay. Now, that problem set that I gave you also has a table. The table is just for you to summarize the discoveries of all the scientists that we went through: Democritus, Dalton, J.J., and Rutherford. So the year, not so much important to me. The experiment is the research. So J.J. was the cathode ray, Rutherford was a gold foil, Dalton was the atomic theory, Democritus was the atom is indivisible. Then the models, Democritus was a solid sphere, Dalton was a builder, J.J. Santos was a plum pudding, and Ernest Rutherford was the nuclear atom. And then if there's any limitations, I kind of will give it to you. Democritus, he had no experiments, so he doesn't really know how he come up with what he said. Dalton he didn't talk about particles. JJ, the problem was that he said I was a solid sphere, so he didn't account for that solid sphere to have a dense nucleus, and everything else was empty, so he didn't account for the empty space. And Rutherford cannot explain why electrons are not attracted to protons. You have two different particles, two different charges. So electrons, because they're negative, should be attracted to protons. So the electrons should be going towards the center of the atom, but it doesn't do that. They stay where they are, floating around that center, doing, well, they do a lot, but they're not doing anything in terms of being of the attraction. So we have to explain why is that. We're not there yet. So again, from the table, all I am looking is basically what each scientist said and what they discovered. If you can remember that, you will be okay with the questions you might get. Okay, so those are the type of questions you should be able to see in this chapter so far. Calculate particles, calculate the weighted atomic mass of the isotope of the element based on the isotopes, compare the experiments, and that's pretty much it. The rest of the chapter we'll do on Thursday, which is how to name compounds, and that's pretty straightforward. It should be pretty easy. Now, the only thing from chapter number 2 that we haven't done yet is talk about